This is my second video from section 7.2, and we're going to talk about another calculator operation. We're also going to find this. This is going to be in your dist button, which you will get by pressing second vars. If you press that, you'll be in the distribution menu, and we're going to choose, well, it actually depends on your calculator. This could be choice 2 or choice 3, but in either case, it's going to be labeled inverse norm. So again, I'm doing another continuous random variable, but I don't care what x is representing. But I do know what the mean is. I know, hang on. The mean I have just randomly decided is going to be 50, and the standard deviation is going to be 7. These are the same values we used in the last video. And here's what we're going to do. We're going to find the x value such that the area under the curve to the left of it is 0.1. Now, definitely, without a doubt, draw your picture so you can figure out what we're talking about here. We're looking for an x value. The mean here is at 50, and the area to the left is going to be 1/10 of the total area here. So my x value is going to be somewhere around here, and this area here, this equals 0.1. So what we're doing is the opposite of what we did in the last video. Last time we knew the x value and we were trying to find the area under the curve, the probability. This time round we know the area under the curve, which is equal to the probability. The probability of being some value less than this value is equal to 0.1 because probability is area under the curve. What we don't know is what's my cutoff value. We're talking about all the values less than what? And that's what we need to find. So we've swapped the inputs and the outputs. We need an inverse function for normal CDF. And you may have already guessed it, that is inverse norm. Okay, so let's talk about inverse norm, what goes into it. The inputs for inverse norm are, let's see, we have inverse norm. If you have in your calculator, then you have the following choices: area, mu, and standard deviation. And then when you've got all that in there, you're going to paste. And if you have an older calculator, your inverse norm is going to look like this. When you select inverse norm, you'll get this on the screen, and it'll open a parentheses, and it's going to ask for area, mean, and standard deviation. But this area is always going to be area to the left. So luckily, we are talking about, here's x, we're talking about the area to the left is 0.1. So on this version of the problem, it's fairly simple. It's going to be 0.1, mean is going to be 50, standard deviation is going to be 7. On a older calculator, it'll be inverse, hang on, I'm running out of space here. Inverse norm, 0.1, area to the left, mean is 50, standard deviation is, standard deviation is something specific. It is, in this case, it's 7. And if we pop all of that loveliness into your calculator, what you're going to get out, whether it's an older calculator or it's a newer calculator, I have it written down somewhere. Oh, it's right in front of me. It is going to be, our x value is going to be 41.03. I rounded that a little bit. So this value here, here was the mean. Oh my goodness. And this value here is going to be 41.03. So that was the answer we were looking for. But this question does get a little bit harder, of course. So let's clear the screen and try another version of this question. Okay, here's what we want now. I want the x value such that the area under the curve to the right is 0.025. What does this look like? And here is the mean, And by the way, I know the mean is dead in the middle of my normal distribution. So I know I've got 50% over here and 50% over here. So 25% is going to look something like that. So this is the x value that I'm trying to find. And the area of this shaded area here is 0.25. Well, my calculator wants inverse norm. It wants area, but when it says area, it means to the left. And then it wants the mean and the standard deviation. Those are the easy parts. So area to the left, what is that going to be? If this is 0.25, this area over here to the left of the cutoff is going to be 1 minus 2.5 because total area is 1. So this will be, area to the left will be 0.75. The mean has not changed. The standard deviation has not changed. So when I paste this, this will be, x is going to turn out to be 54.72. In the older calculator, what this looks like is inverse norm. And you know, your calculator is pretty smart. You don't actually have to compute what 1 minus 0.25 is. You can just put that in there, and it'll figure out that that's 0.75. 50 and 7. It still gives you 54.72. Okie dokie, let's go one harder here. So this version of the problem is asking for two x values. And I really can't emphasize enough the importance of drawing this picture here. So here's my normal distribution, and I'm talking about the middle 94%. So I'm talking about, hang on. So what we have here in the middle here of my normal distribution is 94% of the curve, which I'm going to decimalize 0.94 is the area between these two markers. I want two of them, so let's call this guy x1 and let's call this guy x2. Let's start on x1. So if I've got 0.94 in the middle, these two combined had better add up to combined is 1 minus 0.94, in other words, 0.06. So that means just in the left-hand tail, because it's symmetric and this is dead in the middle here, this area to the left is going to be 0.3. So to find x1, x1 is going to equal inverse norm 0.03, comma 50, comma 7, which is equal to, where do I have this written down? This is equal to, oh man, what do I have here? 63, no sorry, that's the other one, is equal to 36.83 after rounding. Now to find x2, let me do a little bit of erasing here. To find x2, the area to the left of x2, well, we've got two areas to the left of x2. We have here 0.03 and we have here 0.94. Combined, what I have to the left of x2 is 0.97. So x2 is going to equal inverse norm 0.97, comma 50, comma 7. So you do see the advantages, I'm hoping, of drawing a picture so that you can work your way around this problem spatially. And so what x2 is equal to is 63.17. Okie doke. So what I want you to do right now is I want you to do, which exam? Sorry, so what I would like you to do is do example 3 on page 370, and then come back to me when we're done. And by the way, do only focus on the tech approach. We are skipping using tables. We're not skipping finding z-scores though, so we will get to that in the next video. Okay, here's our last set of examples, and yes, it does just keep getting tougher and tougher. What is the 80th percentile? Do you guys remember? What does this mean? Oops, come back. The 80th percentile means the x value that has 80% below it. The x value that has 80% below it. Oh no. There we go, got it. Okie dokie, so here we go. 80% is more than half the graph, so this will be a little bit to the right of the mean, which is 1060. So here's our unknown x value, and below it is 80% of the data. In other words, this area here is 0.8. So it's interpreting the question is the hard part. So we're going for inverse norm. The area to the left is 0.8. The mean is now 1060, and the standard deviation is 195. And I do have this answer somewhere. It is the SAT score that's the 80th percentile is 1,225. Okay, let me ask you another question. Okay, so what is the cutoff for the top 10%? So what does that look like? Here's your normal distribution. If it's normally distributed, that says to me bell curve. The mean of 1,060. 1,000, okay, hang on. 1,060, that's what that says to me. The top 10%, I'm talking about the top 10%. The pen's getting tired. That's this area here, but don't forget, inverse norm needs area to the left. So that's going to be area. So if we've asked for inverse norm, we're going to put in area, we're going to put in 90%. And then the mean will be 1,060, the standard deviation will be 195, and somewhere I have this answer. It's going to be that x is going to turn out to be 1310. So that's the last of my video on inverse norm. I am still hoping to make a video on the standard normal distribution and also a video on critical values. Keep watching.